Okay, so welcome back to a new lesson, testing your control interfaces. So your robot now has control interfaces, or the muscles, and now we're gonna wire it up, and we're gonna use a small Python script to command all the steering and drive joints. Okay, we are also gonna learn a little bit about how to organize your packages, and we are going to also see why eventually we're gonna need some more complex drives. So, the learning objectives, we're going to verify that the control interfaces and the controllers actually move the robot in simulation. We're going to understand the package split, how to organize your packages. This is very important as your project grows. And so we're also going to learn how to publish all of these steering and drive commands in a group. And then we're gonna see how once we start trying to turn left, we observe the need for more complex drive model kinematics that we have to implement. And we will implement later in future lessons. So let's begin. So let's talk about the packaging, right? So our project is growing larger and larger, and there's a need to organize it in a specific way. So we will have a control package where we are going to basically put everything related to control. And if we look inside, we have configuration files for different controllers. We have a launcher for a swerve controller that we're gonna be working on in future lessons, so don't worry too much about it right now. And there is also code that we're going to use to test our controllers. Okay, and we will be working one of these in this lesson. So this is for control. Everything about control is there. Now description, everything about the body of our robot, the look of our robot, or it's there. So the URDF or the different URDF we've been using, especially in module 1. Now RVIS configurations to display the robot in RVIS is there. And we also have our meshes, so basically the sensors, the battery, all these things that cannot be modeled by URDF. And we have different launchers to show a robot at different stages throughout the lessons. And it's important to put all of these visuals and basically the body of the robot in the description package. And then we have a gazebo package where we're gonna be launching our simulation. So basically, it's all about simulation here, and we have launchers for launching gazebo with different worlds, and we're gonna refer to our description and control from the gazebo launchers. Okay. Right now we don't have scripts, but we may have, and we don't have special worlds, but we may at some point create worlds and we would put them there. So basically that's it. Later we can have other more complex controllers like the swerve controller, but don't worry about it right now. But in general, you have to separate all the different things in different packages to keep everything organized, especially as our projects become bigger. So we have control, everything control is there, everything description is in description, everything simulation is in gazebo. This is a standard practice for ROS. Okay, so before we move forward, I think it's important to do a quick review or a quick learning for some of you, or review for some of you, of ROS 2 nodes and topics. So this is not a ROS course, right? But it's important that we introduce these things briefly, and this is particular for Humble. It's part of the official lessons or tutorials. So nodes are basically different ROS2 programs, and they communicate with each other using topics. So for instance, one node can be the controller, another node can be a broadcaster, another node can be RVIS, and they would talk to each other using topics. So one can publish information through the topic, and for instance, this could be the the Python script that we're going to be working on soon, publishing drive commands, and the subscriber can be the controller for the drive joints that listens to these commands and moves the robot. So again, this could be our Python script pushing data to the controllers, and the controllers subscribing and listening to that data. Okay, so let's try that. Let's try it. And also we're gonna see a little bit more of ROS2 stuff right now. So first, let's go to the workspace. Let's build it again, if you haven't. And never forget to source the workspace. And let's launch our Gazebo simulation. So we go to the Gazebo package. Remember, everything is there. And TP1 launch. So we've seen this before in the previous lesson. And let's just confirm that everything is working and talk a little bit more about certain things that we didn't talk about last time. So I want to list the nodes again. All the nodes that we previously saw are there. But I want to talk about ones in particular. So again, the topics are there as well, topics for drive, control, and steer control. But I want to talk about the joint states topic. I didn't talk about it in the previous lesson. So let's inspect this topic. Let's use ROS2 topic info -v for verbose. It's going to show additional information in joint states. And here we can see information about this topic. Okay, so the type of this topic is sensor messages, joint state. Remember, it's a sensor, right? So it's feedback. And the publisher is the joint state broadcaster. Remember, we talked about this broadcaster before. It will publish this joint state, and the subscriber, or the node that subscribed to it, is the robot state publisher, which is in charge of publishing all of this TF data that we can visualize in RBase there below. So again, the joint state broadcaster is a sensor. Think of it as a sensor that will post everything about the joints, the state of the joints, and the robot state publisher subscribe to that data, and we can visualize the state of the joints in RBase. So let's try it. We're going to publish velocity commands to all of the joints, the drive joints. So, once. I just want to publish it once. And the topic is all steer position controller. And then commands, right? Where did I make a mistake here? Velocity. All drive velocity controller, yeah, and then commands. I think I was looking at the wrong topic. All drive velocity controller commands, and it's of type float64 multi-array. And here's the layout. So we're gonna fill in the data field with velocities of positive 1.5 meters per second for all of the wheels. This will make the robot move forward in a straight line. So when I send this data, you'll see that immediately the state broadcaster will sense and broadcast the state of the joints. The robot state publisher will catch that and will update the TF tree, which we can visualize here in RBase. You see those coordinate frames, right? The red and the blue thing moving there, axis moving there. It's the TF tree being updated. And then we can see that the robot in simulation was actually moving. Something else we can see to make it more clear, we can actually echo the topic where the state is being published. So it's, let's find out. I always forget these things. ROS2 topic echo. Joint states. And if you look at that, there's the data being published by the state broadcaster. So if we expand this window a little bit, you see there are all of the joints there, and all of their positions and all of their velocities. Remember that our broadcaster is giving us information of velocities and positions. So for every joint, we can sense, or we can obtain their position and their velocity, and you can see that it's changing, right? It's changing because our wheels are spinning. We can also see what the robot state publisher publishes, which is related to TF on the transformations. So yeah, ROS2 topic echo TF, and you can see there it's a very long topic, but we can see parts of it. Like you can see some of the joints there being published, and you can see how they're rotating. Some of them are rotating, some of them are translating. I think they're rotating. So yeah, you can see the TF. That's why you can see the wheels spinning in Arvis, because the TF is being updated by the robot state publisher. Anyway, so we can confirm that everything is working. We can control our robot. Confirm. So let's run it again, because now I want to test the Python script. So I reset everything, and I'm going to try to organize the windows a little bit. I'm very bad at this, but I'm going to try to organize the windows sorry, so that we can actually see what's going on. And I'm going to run ROS2 run. There's a difference between launching and running, but again, this is not a ROS2 course, so please take the tutorials to learn the difference. Yeah, need to source before, otherwise we can't find the scripts to run. And then in control, we're gonna run this test robot control script. And once we run it, we'll see that we're going to center the steering. Then we're gonna, let me start this again. I want you to also see Arvis. So sorry about that. Let's start this again. Organize the windows a little bit. Very bad at organizing windows, but let's organize the windows a little bit so that it's easier to see. And let me move this up. Let me run the script again. Okay. And then there you go. So we're gonna first center the steering, so all wheels are centered. Now we're gonna turn all wheels left, so you see the wheels turned both in Arvis and in the simulation. Now turn them all right, and then we're gonna center them again and move forward. Okay, and you can see all of the commands there being published, all of the steering and the driving commands. Now we stop. Now we're gonna do an Ackermann turn left. So you see how, you see how the robot is turning and moving forward. Not just turning, but turning and moving forward, and then stop the robot and center the steering. Let's run this one more time. So turning left, turning right. Then all wheels will be centered and then driving forward. So you see the robot driving forward. And again, notice all of the commands being sent to the joints. And now we're going to do the Ackermann turning left. I want you to pay attention to this. Look at the wheels and their angles. They're different, right? And they are moving at different speeds. And the robot is turning and moving forward at the same time. So again, you can see all of the commands being sent there. Now let's have a look at the code. And so in control, where is it? There. And test robot control pi. So let's have a look at this code. So here, this is just a node, ROS2 node. Let's make the font a little bit bigger. So it's a ROS2 node. So let's look at the publishers. So here we have a publisher that will publish to the all steer position controller commands, one for the all drive. Let's close this. All drive velocity controller, so to control the steering and the drive. So two publishers. Then we have some helper functions there. Then we have Yeah, the helper functions. Then we have a function for stopping the robot, which just means send drive values of 0, stop of the wheels from moving. Then center steering means set all angles to 0, so we center the steering. And we have functions for that, right? We have the set steering, set drive, and we can send the angles or the velocities to them. So here's the main code. So we first center the steering. Again, it's just setting all the angles to 0. Then to turn the robot left, we convert 30 degrees to radians using some math package. So 30 degrees to radians, and then we set all of the angles to that. Then to turn right, we do the same, negative 30 degrees to radian, and then we set all of the angles to that. Now to center and drive forward, what we call the center steering, and we set all of the velocities of the wheels to 2 meters per second. Then we stop the wheels, and here's the interesting part. To do the turn left, or the Ackerman turn left, we set the angles to different angles. So we see 30, 25, 15, 12, 5, 4, no single angle anymore. So we set the steering to all of these different angles, and even the velocities of the wheels are different. So all the wheels move in different speeds. So different angles, different speeds, just to make this left turn, like we're turning and moving forward at the same time, like an Ackerman drive type of vehicle. So and then we just stop everything. So what I want you to understand is that once we try to do things more complex than just moving forward and stopping, we need to set all the different things to different values. So let's look at this for now. So pause. So actuation, right? We have all of these topics for sending commands or controllers, and feedback or sensors. We have all of these topics for sensing data. And then back to what I was talking about earlier, we have multiple types of robots with multiple types of drive models. We have Ackerman, differential, swerve, which is our own SHL1 robot. We later will implement a swerve controller for 6 wheels. But there are different kinds of drive models, right? And it depends on the geometry of the robot. Some robots have 2 wheels, some robots have 4 wheels, or like Ackerman, they only the front wheels move or only the back wheels move. So there's a large variety of drives, and they're all very complex. They all depend on the geometry. Swerve is what we have, SHL1. We're gonna implement later a swerve controller. So back to this, different angles, different speeds, and this requires, we can't just guess these values, because there are so many different ways in which we can turn and do things. So we can't just manually send them. We need specialized drive models or drive controllers for these robots. And in particular, SHL1 has 6 wheels, is a swerve drive. We need a custom drive for it. And in a future lesson, we're going to learn how to build such drive. So see you soon.